In today's video lecture, we're going to continue to look at RC and RL transient circuits, but we're going to add a wrinkle. If you recall, until now we've looked at circuits where after time t0 there is no source present. Either it is turned off or switched out of a circuit. Today we're going to look at driven RC and RL circuits. In a driven RC or RL circuit, there is still going to be an abrupt change at time t0. But the big difference from before is that a source will be present. It will either be turned on or switched into the circuit at time t0. Before t0, there may or may not be a source present. But after t0, there definitely will be a source present. The big difference in the differential equation is in this term here. Before, if you recall, f of t was always 0, so we only had a homogeneous solution. Now, f of t is going to be a constant. Specifically, it is going to be the value of the source after t0. Actually, source or sources, there could certainly be more than one. Value of source or sources after time t0. So if you look at the solution now, the total solution is the homogeneous solution we saw before plus an additional term, which is the particular solution or the forced response, as we like to say in engineering, and it just happens to be the steady state value of the variable at t equal infinity. Once again, the homogeneous or the natural response is the same type of exponential decay that we saw in source-free circuits. So what effect will the presence of a source after time t0 have on the shape of the response? Well, you're still going to have the transient response due to the homogeneous part of the response, but the presence of the source after t0 will mean that the voltages or currents, whatever you're measuring in the circuit, will not decay to 0 as it did in the source-free case, but instead it will be forced to a new steady-state value after the transient dies down. This opens up a whole bunch of possible different shapes for the response. I'm just going to draw a couple of them here. For example, you could have a situation where whatever variable we're looking at starts at 0, and then at time t0, which once again does not have to happen at 0, it exponentially rises to a steady state value. You could also have a situation where you start off with some steady state value up to t0, and then at t0, the value exponentially changes to a new non-zero steady state value. You could have a situation where you start off at one steady state value, change in the circuit at t0, and the value goes from here, maybe down to here. So once again, depending upon what x of t is, you could even have a situation where there's a discontinuity in that variable at time t0. You could have a situation where you start off where x of t is negative, and then it immediately jumps to a positive value and maybe even decays to another negative value at infinity. You could have a situation where you start off negative, and it goes exponentially up to some positive value. And you could certainly have a situation where maybe you start off at 0. It jumped to some positive value and then exponentially approaches some new negative value. So these are just some of the many different shapes that you could have. And as I said before, notice in some cases there could be a sudden discontinuity, a sudden jump in the variable x of t at time t0. And in other cases, there may not be, and that really depends upon what the variable x of t is, as we will see in some of our examples. In all the cases, though, we're still going to have this exponential shape, sometimes going up, sometimes going down. All right, let's look at the equation a little bit. We know from before that the homogeneous response xh of t is always going to be some constant k times e to the minus t naught over tau. We also know that because we now have a forced response, our total response x of t is going to be the forced response x sub f, which is just a constant, plus k times e to the minus t naught over tau. In the case where we had source-free circuits, this k was the initial condition in the source-free case. But we're going to see it's not quite so simple in this driven case. If we plug t equal t naught into that equation there, we see x of t naught plus equals x naught. This is our initial condition, which equals x sub f plus k e to the minus t naught over tau. Of course, e to the 0 is always 1. So now we see that k is not x naught, but it's x naught minus xf. So our final solution for t greater than or equal to t naught is x of t equals the final value plus initial minus final times e to the minus t naught over tau. Once again, that is our final value, and this is our initial value. So let's revisit the algorithm for driven RC and RL circuits. Just like in the source-free case, you need to first find VC and IL at 0 minus, and that's going to be a DC steady-state problem. Second step, which is one of these steps that you may or may not have to do depending upon the problem that you're solving, is if you're looking for a variable x other than VC or IL, find that value also at t naught minus. Third step is also the same. You redraw the circuit after the discontinuity. And just like in the source-free case, we know that the value right after the discontinuity of VC is unchanged, or the value of the current through the inductor at t naught plus is unchanged. Step 5 is a new step. In the driven RC or RL case, we have a second DC steady-state problem to solve. Specifically, we need to find the voltage across the capacitor at infinity or the current through the inductor at time infinity by solving a second DC steady-state problem. Step 6 then is we need to find the time constant associated with the circuit and then plug everything into the equation here. Probably the easiest way to find the time constant, just like the source-free case, is to Thevenize the circuit around the capacitor or the inductor to find R Thevenin and then set time constant equal to the capacitor times R Thevenin or the inductor divided by R Thevenin. Once we have all that, we can find that the voltage across the capacitor is the final value, which we got in this new step 5, plus the initial value, which we got in step 4, minus the final value, times e to the minus t naught over tau, where tau we got there. Likewise, if we're looking for the current through the inductor, we have a final value, which once again comes from step 5, plus initial minus final, where initial comes from 4, final comes from 5, times e to the minus t naught over tau, where tau comes from there. Step 7, like step 2, is a step we may or may not need to do depending upon what x is. If the variable that we're ultimately looking for is something other than Vc or IL, we find an expression for it as a function of Vc or IL, which we already have now, to find an expression for x of t. And once again, this step plus step 2 we may or may not have. So let's look at the final form of the equation and also what the graph looks like. Just like in the source-free case, we're going to have two different situations. We're going to have for t less than t naught, the value of our variable is just going to be a constant. And for t greater than or equal to t naught, we're going to have this exponential decay plus some final value added together. X of t is x final plus x naught minus x final times e to the minus t naught over tau. If you look at the graph of x of t, we're going to see that there are 5 distinct pieces of information that we need to have in order to draw it. The first one is the value of the variable we're looking for before the sudden change in the circuit. This is going to be a DC steady state value. Second piece of information is the time of the change in the circuit. This is the time where a switch is thrown or a source is turned on or a resistor is added or a resistor is taken away, where there's some change in the circuit that's going to cause the transient response. This is usually given in the problem itself. The third thing you need to find is the value of the variable right after this change in the circuit. And, as before, depending upon what this variable x is, it may or may not be allowed to be different from x of t naught minus. The fourth piece of information is a new one, and that is a new final value for our variable. In the source-free case, this value was always 0, so you could ignore it. In this case, it is not going to be 0. Final piece of information is how long it takes for this transient response to settle down. This is related to the time constant. Remember, the time constant times 5 is the time it takes for the transient response to end. Let's do a whole bunch of examples now to show the algorithm for driven RC and RL circuits. And what we're going to see is it's not terribly different from the source-free case. There's just a couple little wrinkles we need to worry about. So in this problem, we have a capacitor, a couple resistors, a voltage source, and a switch. The big difference from before is notice the direction of the arrow. In this case, the voltage source and 50 ohm resistor are being switched into the circuit at time 0. So our change in the circuit is at time 0, but now rather than discharging the capacitor after 0, we're actually going to be charging the capacitor. So this is a charging capacitor problem. So you draw the circuit at 0 minus, and here's a pretty boring circuit. At 0 minus, you just have a resistor and a capacitor. The capacitor is in DC steady state, and it's pretty obvious to see that VC of 0 minus is 0 volts. You redraw the circuit for t greater than or equal to 0. Now, the voltage source is present. We have a 50 ohm resistor here. We have this 50 ohm resistor here. And this capacitor is not in DC steady state. We need to find two different things at this point. We need to find VC of infinity, and we need to find the time constant. The easiest way to do this is probably with one step. If you take the whole circuit as seen by the capacitor and find its Thevenin equivalent, you can then find VC of infinity and tau virtually from inspection. So if you look at VOC, that's an open circuit voltage as seen by the capacitor if the capacitor is removed. VOC is just 50 over 50 plus 50 times 20 volts. Or 10 volts. Our Thevenin, you remember how you find the Thevenin resistance of a circuit. You turn off all independent sources. Our Thevenin now is a 50 ohm resistor in parallel with another 50 ohm resistor. So for t greater than or equal to 0, our circuit looks like this. The reason we wanted to do this, the reason we wanted to come up with this Thevenin equivalent as seen by the capacitor, is VC of infinity is now trivial. It's 10 volts. It happens to be VOC. Likewise, the time constant is just C times R Thevenin. So it's 40 microfarad times 25 ohms, or 1 millisecond. Is this the only way that we could find VC of infinity and tau? No. But I think that using Thevenin's theorem is probably the easiest way to find those. We can now put everything together to find an expression for VC of t. It was 0 volts for t less than 0. And the equation for t greater than or equal to 0 is the final value plus initial minus final times e to the minus t over tau, which we can rewrite as 10 times 1 minus e to the minus t over 0.001 volts. We can now plot VC of t. We see that its value before 0 is going to be 0 volts because the capacitor is not attached to any voltage sources. At time 0, the voltage source is switched into the circuit, and now the capacitor starts charging. It eventually gets up to 10 volts. How long does it take to get there? It takes 5 time constants. And if you look at this plot, we have the x-axis as normalized time, so it is going to take 5 time constants, or in this case 5 milliseconds, to get there. And this is where we're going to have, once again, this exponential shape. Final point I want to make is regarding the value of the voltage across the capacitor at one time constant. If you recall, in the source-free case, we saw that when the capacitor discharges, it's always 37% of the initial value after one time constant. Well, that 37% still shows up here, but it shows up slightly differently. What happens is, over the course of the charging of the capacitor, it's going to go from 0 volts all the way up to 10 volts. It goes 63% of the way within the first time constant, leaving 37%. So it goes 63%, leaves 37%. Then between one time constant and two time constants, once again, the total amount there is that, and it's going to go 63%, leaving 37%. So what happens is, every time you progress another time constant, it gets 63% of the way closer to the final value. By the time you get to 5 time constants, it is virtually there. Technically, this function never equals 10 volts. But nevertheless, we say that after 5 time constants, it's virtually there. So you could find an expression for the value after one time constant. Vc at t equal tau is the old value plus 0.63 times the new minus the old. By old, of course, what I mean is the value at 0 plus. By new, I mean, of course, the value at infinity. So in this particular example, this would be 6.3 volts. Let's do another example. This circuit's actually much simpler than the one before, but the source itself is a little more complicated. So now we have a voltage source Vs of t is a minus 2u of minus t plus 4u of t, and a series resistance 500 kiloohms and a 2 microfarad capacitor. The first thing we want to do in this case is plot Vs of t, so we have an idea of what is going on. So for t less than 0, you have that. So it's minus 2 volts. At t equal to 0, that part turns off, and instead a plus 4 volt source takes over. So the shape of Vs of t looks like that. If you're observant, you'll notice that you could also have written this voltage source as minus 2 plus 6 u of t volts. In this first expression, we have 2 unit steps. So this part exists only for t less than 0. This part exists only for t greater than 0. In the second expression, this part always exists, and then at time 0, we're adding 6 volts to it. So minus 2 plus 6 is 4 volts. Anyway, going back to our problem, What we see now is we have a source that's always present, except it changes at time 0. So once again, these driven RC and RL circuits don't have to be situations where you have no source present before 0. You could have a situation where the source changes at time 0. So t equals 0 minus, it's a DC steady state problem, fairly simple one. The capacitor is a open circuit, and VC of 0 minus is just negative 2 volts. Of course, this also means that VC of 0 plus is negative 2 volts. For t greater than or equal to 0, the circuit changes. We still have a voltage source, but now it's 4 volts. You still have this 500 kilo ohm resistor, and then you have a capacitor. Notice in this case, there's no need to Thevenize the circuit as seen by the capacitor. It's already the Thevenin equivalent. So we can directly see what VC of infinity has to be. VC of infinity eventually is going to be 4 volts. Furthermore, we can see tau. The time constant tau is the Thevenin resistance seen by the capacitor times the capacitor itself. So 500 kilo ohms times 2 microfarad happens to be 1 second. We can put everything together. So VC of t has 2 distinct parts. It's minus 2 volts for t less than 0. For t greater than or equal to 0, it's going to be VC of infinity plus VC of 0 plus minus VC of infinity e to the minus t over tau. And this second expression could be rewritten as 4 minus 6 e to the minus t volts. If we wanted to plot this, the value of the voltage across the capacitor, this is our initial value of minus 2 volts. The final value is going to be 4 volts, and it's going to take 5 time constants to get there. Notice, once again, we have normalized time here, t over tau. Of course, in this case, tau is equal to 1, so it doesn't matter. And we're going to have, starting at time 0, this exponential rise to the final value. How about the value at 1 time constant? Once again, over the course of 5 time constants, the voltage across the capacitor will rise from minus 2 all the way up to 4 volts. It's going to do 63% of that moving during the first time constant, leaving 37%. So 63% there, 37% there. So the value after 1 time constant, so VC of 1 is what? It is the old value, which is minus 2, plus 0.63 times the new value, the final value, minus the old. And notice there is a minus here. You have to be careful about that. You work out this math, it's approximately 1.78 volts. So another way to look at it is after 1 time constant, The voltage across the capacitor got 63% of the way to its new value. And once again, between 1 and 2 time constants, it would travel another 63% of the way there. Between 2 and 3, another 63% of the way there, etc., etc. Technically, it would not get to the new value until infinity, but after 5 time constants, in this case 5 seconds, for all intents and purposes, it is there. Let's look at another example. This is a little more complicated. We have 2 different voltage sources. The voltage source on the left gets switched into the circuit at t equals 0. So a sudden change in the circuit. At the same time, this voltage source turns off. So this problem's a little more complicated because we have 2 sources, one of them controlled by a switch, switching in, switching out physically, the other one turning off at time 0. Way to analyze it: you start off by drawing the DC steady state circuit at 0 minus. The 80 volt source on the left is not part of the circuit, so we just have a 24 ohm resistor here. We have the 12 ohm resistor here. The capacitor is an open circuit. So the voltage across the capacitor looks like that. There's no current through it. 4 ohm. 100 volt source. To find VC at 0 minus, we could use voltage division. The voltage across the capacitor is that resistance over that resistance times the 100 volts. So VC of 0 minus is equal to 12 plus 24 over 12 plus 24 plus 4 times 100 volts, or 90 volts. Likewise, VC of 0 plus has to equal VC of 0 minus, because the voltage across the capacitor cannot change instantaneously. That is also 90 volts. For t greater than or equal to 0, what does the circuit look like? Now this 80 volt source is present. We have our 24 ohm resistor, our 12 ohm resistor. The capacitor is no longer an open circuit. We have this 4 ohm resistor, and now, because of this unit step function here, the 100 volt source is off. But because it's not switched out, it's just turned off, it now becomes a short circuit there. What this means is that this 4 ohm resistor will have an effect on the circuit for t greater than or equal to 0. If there was a switch here, if there was a physical switch removing this source, then that 4 ohm resistor would not have an effect. Once we redraw the circuit, we want to basically find the voltage across the capacitor at our new steady state value VC of infinity. We also want to find the time constant. So 2 things we need to find. We want VC of infinity, and we want to find tau. There are multiple ways we can do this, but perhaps the easiest way is once again finding the Thevenin equivalent as seen by the capacitor. In other words, find VOC and R Thevenin as seen by the capacitor. To get VOC, we take the circuit on the bottom left there and redraw it. With the capacitor once again open circuited, and that is our VOC. 24, 12, and 4 ohms. If we did KCL at that node, sum of that current plus that current plus that current is equal to 0. We get, calling that ground, we get VOC minus 80 over 12 plus 0, that's the current going down, plus the current to the right is VOC minus 0 over 4 is equal to 0. You get 4 VOC over 12 is equal to 80 over 12, or VOC is 20 volts. If you wanted to find R Thevenin, the voltage source is replaced by a short, 24 ohm, 12 ohm, 4 ohm. Well, we see because of this short here, this 24 ohm resistor has really no effect, and our Thevenin is just 12 in parallel with 4, or 3 ohms. So our Thevenin is 3 ohms, VOC is 20 volts. From that, we can determine that VC of infinity just happens to be VOC, or 20 volts, and the time constant tau is going to be 3 ohms times 2 farads, or 6 seconds. I should point out that this is not the only way that you can find these two values. You do not need to Thevenize the circuit necessarily, but I find that it's usually easiest after you redraw the circuit for t greater than or equal to 0, find its Thevenin equivalent, because then you can directly read off what VC of infinity is and directly read off what the time constant is, because you have our Thevenin. Continuing on, we can now find an expression for VC of t. It equals what? Before the discontinuity in the circuit, before the change in the circuit, it's 90 volts, a DC steady state value. What's the value after the change in the circuit? It's VC of infinity plus VC of 0 minus VC of infinity e to the minus t over tau, which you can rewrite as 20 plus 70 e to the minus t over 6 volts. If we wanted to plot this, we have a DC steady state value, a change in the circuit at time 0. It's going to take 5 time constants to get to the new value, and once again we are using a scaled time axis. The final value is going to be 20 volts, and it will take 5 time constants to exponentially get there. If we were asked to find the value after 1 time constant, once again the voltage is going to go from 90 down to 20. It's going to do 63% of it in the first time constant, leaving 37%. It's going to travel 63 and it's going to leave 37. So the value here, so VC of t at t equals 6 seconds, which is one time constant, is going to be what? The initial value plus 0.63 final minus initial, or 45.9 volts. In the next lecture, we will do a couple more examples of driven RL or RC circuits, and then we will look at a situation where you have multiple discontinuities. By multiple discontinuities, we mean you have a circuit that doesn't change just once, but maybe 2 times or even more than 2 times. Have a good day.